Hey everyone. In this video we're going to talk a little bit more about circular motion, and in particular we're going to talk about what has to happen to cause circular motion to happen. So to start off with, I'm going to ask a question here. Let's say we have an object which is traveling in a perfectly circular path at a constant speed. So that means both the linear speed and the angular speed are constant for this object. So my question for you is this object accelerating? All right, so I'm not going to answer that right away, so just think about that question, see what you think your answer would be, and then as I go through this video, we'll figure out what the answer is. Okay, so next question I'm going to ask is seemingly unrelated, but let's just say we have an object traveling in a straight line. So it's moving with some velocity v, and let's say there's a force acting on the object which is in the same direction as the motion. So if this object is being pushed by this force, what is going to happen to the motion of that object? Right. So the answer is, if you push an object in the same direction that it's already moving, it is going to speed up. What about if we have an object which is traveling in a straight line with speed v, and there's a force that pushes it in the opposite direction of its motion? What would happen to this object? Right. Well, if you push an object against its motion, that's going to cause the object to slow down. And if the force acts long enough, eventually the object would stop and start accelerating in the other direction. All right. So now we can ask, what happens if the force is acting in some other direction? So specifically, what if we have an object which is moving in some direction, and there's a force which is perpendicular to the motion? Okay, so what do you think will happen to this object? Okay, so for this object, the force is not pushing it forward in the same direction of its motion, but it's also not pushing it backwards. So this object is not going to speed up or slow down, but something will happen. As you can imagine, the object is going to curve. So its direction is going to change, and it's going to start moving in a different direction like this. And it's going to curve towards the direction that the force is pointing. Right. So this object turns or changes direction. So you can see a force can have more than one effect on an object. It can change its speed if it's pointing, either forward or backwards relative to the direction of motion of the object, but it can also cause its direction to change. So let's go back to this original question. If an object is moving in a circle at constant speed, is it accelerating? And the answer to that question is yes. So to understand why this is, we have to understand that in physics, acceleration means something different than it does in everyday language. You usually think that acceleration means speeding up, but in physics, it can mean speeding up, or it can mean slowing down, or it can mean changing direction. So remember, velocity is a vector, and the true definition of acceleration is that acceleration is defined as a change of velocity. Since velocity is a vector, it has both a magnitude, which is speed, and also a direction. So when we say the velocity is changing, that can mean it's changing in speed and or direction. If either of those things changes, then the object is accelerating. So an object traveling in a circle, even though it's going at constant speed, it is not moving in a constant direction, so it is always accelerating. All right, so another question we can ask is, now that we know the object is accelerating, what is the direction of the acceleration? Well, if you think about this third example that I gave you, if an object is pushed, sort of to the left so to speak, then the object will curve in that direction. So let's say this object moving in our circular path, let's say it's going counterclockwise around the circle so that its linear or tangential velocity at the 3 o'clock position is pointing straight up. Which direction would you need to push on this object to get it to curve around this circle? Would you push it to the right, towards the outside of the circle, or would you push it to the left, towards the inside of the circle? All right, so hopefully you decided that you should push the object in this direction to get it to curve to its left so that it goes counterclockwise around the circle. So the force is always going to point towards the center of the circle. And that's why we give it this name that's written up at the top, centripetal force. Centripetal means center seeking. So if you just remember that, the word centripetal sort of has the word center in it. It means center seeking, so that means the force is always pointing towards the center. All right, so we know the direction of the centripetal force. What about the magnitude of the force? How much force does it take to get this object to move in a circle? Well, that's going to depend on 3 things. So let me redraw a circular path down here. So let's say we have an object. Let's give it a mass now m. Let's say it's going around with some speed v, and let's say the radius of the circle is r. The amount of force needed to keep the object moving in this path is going to depend on all 3 of these things. A more massive object needs more force to get it to change direction. If it's going faster, you need more force to get it to change direction. And if you're turning in a smaller circle, it also takes more force. You can understand this if you think about driving in a circle in a car. If you drive your car in a very gentle, large circle, you don't feel much force from that. But if you turn a really sharp circle, or if you take a turn really fast, then you're going to feel a lot more force. All right, so the formula for centripetal force, we're going to call it Fc for centripetal. It's equal to the mass of the object multiplied by the velocity squared divided by the radius. So this is a formula that you should write down. All right, so that's the force. What about the acceleration? Right, this object is accelerating, so how do we determine what the acceleration is equal to? Well, if we compare this formula to Newton's second law, which remember is F equals ma, mass times acceleration, then this part of the formula here must represent the acceleration of the object. So we'll call that AC. This is centripetal acceleration. That is equal to the velocity squared divided by the radius. Okay, so let's look at a couple of examples. Okay, so let's say, sorry to make that an actual circle. Let's say we are spinning a ball on a string above our heads. So here's the ball. Let's say this is a top-down view. So let's say the radius of the string is 50 centimeters, and the ball is moving with a speed of 2 meters per second. Let's say the mass of the ball is 200 grams. All right, so we could ask, what is the acceleration of the ball? All right, so if we remember, acceleration is equal to velocity squared divided by r. That will be 2 squared divided by r. Now r has to be measured in meters as always. So 50 centimeters is 0.5 meters. So that will be 8 meters per second squared. Right, so the acceleration still has the same units as it always does. What about the force? Right. So the force, this is what we call the centripetal force, that is equal to mass times v squared over r. The mass is 200 grams, which is 0.2 kilograms, times v squared divided by r, or we can just take the acceleration, which we've already calculated, and multiply that by the mass, which is 0.2, and we should get 1.6 newtons for the force. Okay, so where does this force come from? One common misconception is that centripetal force is not actually a physical force. It has to come from somewhere. So this formula is really telling you how much force is needed for this object to move in a circular path. So where does that force come from? Well, the ball is going to be attached to a string as it goes around your head, and that string is going to be under tension, and that's going to pull it in this direction. So this is going to be tension in the string that will provide the centripetal force. Okay, so let's look at one last example. Let's say you are driving in a car on a road. So this is a top-down view of a car. Let's say you're on a curve which has a radius of 100 meters, so a pretty large curve. Let's say the car is moving with a velocity of 15 meters per second, and let's say the mass of the car is 1,500 kilograms. So how much force is required to keep the car moving on this path in a circle at constant speed? In other words, what is the centripetal force? So to calculate the centripetal force, again, we take the mass, multiply by velocity squared, divide by the radius. So that is going to give us a force of about 3,375 newtons. So here's a trickier question. Where does this force come from? There must be some force acting on the car which is pushing it in this direction towards the center of the curve. So it turns out that this force comes from static friction between the car and the road. So if this car was on ice and there was absolutely no friction whatsoever, once it was going in a straight line, it would not be able to change direction because there's no friction. So you need to have friction between the car and the road in order to make a turn. That's why when roads are wet, you need to take curves at a slower speed because there's not enough friction and it's not easy to get the amount of force that you need for the car to make a turn. So if there's less friction between the car and the road, then you want to decrease v, your speed, so that you decrease the amount of force that you need to stay in the circle. By the way, let me just address one common misconception here. It's very common for people to think that the force, when you're traveling in a circle, points in this direction. Because if you're in a car and you take a curve very fast, that's the direction that you go, right? You sort of feel yourself sliding towards the outside of the turn. That is actually a result of your inertia trying to keep you going in a straight line rather than turning. But once you are moved up against the side of the car, let's say this is you up against the outside door of the car, that car door is going to push on you, and it's going to push you in the direction towards the center. So there's actually no force acting on you in this direction. There's only a force pushing you towards the center of the turn. All right, so that should do it for this video. Thank you for watching.